Look at the integral theory for real functions. What we're going to do is first define for function f, we define f plus as being the maximum of f and 0, and f minus as being the maximum of minus f and 0. Okay, so you compute f of x, and if f of x is positive, then f plus of x is f of x. If f of x is negative, then f plus of x is 0. That's what we are saying here. And same thing on this side, except that this time it's minus f of x. Okay? So so you should note that f plus is a positive function, and f minus is also a positive function. Okay, you cannot go negative with these functions. Okay, and the notation may be a little odd, it's an f minus, but it's still a positive function. Now, first property, f is actually f plus minus f minus, and absolute value of f is f plus plus f minus. Okay, so that's an important way to look at a generic function by looking at the positive and negative part. How do you prove that? So if your f of x is negative or 0, then f plus of x is 0. And f minus of x is minus f of x. So f of x is f plus of x minus f minus of x. Okay, because we have 2 minus and we get our f back. Okay, and absolute value of f, which in this case would be minus f of x, is f plus of x plus f minus of x. Does it make sense? Okay, and then you do the other case. Okay, the other case is you take fx positive, you compute your f plus, your f minus, and you check that it's true. Okay, so it's similar, and you can just do it as an exercise. So a function which is measurable, okay, on some x and mu is said to be integrable if the integral of the absolute value of f is finite. Okay, so we go back to positive functions. You see, we don't know what to do without positive, actually. So we take absolute value and we call this integral. Okay? Now, in that case, then we define, and the set, so the set of integrable functions is denoted by L1. That's all L1 set. Now, what's the definition? If f is in L1, we define the integral of f as being the integral of f plus minus the integral of f minus. Now, for this to make sense, we need to check something. What? What do we need to check for this definition to make sense? That we don't get infinity minus infinity. Okay, because this is one thing we don't know how to deal with. So we need this, we need to check that. But it's easy because of the following. F plus is either f or 0, the largest one of the two. So f plus is less than f in absolute value. Therefore, the integral of f plus, which is a positive function, is less than the integral of the absolute value of f, and we're assuming this guy to be finite. That's what it means to be integrable for us. And same thing for f minus. F minus is also less than absolute value of f, and the integral of f minus is less than the integral of absolute value of f. And so this is a well-defined definition. This is well-defined. This is not infinity minus infinity. They are both finite. Okay, but that's important. First property, the integral is a linear operator on L1. Okay, a linear combination of integrable functions has an integral which is the linear combination of the integrals. Okay, the usual, right? You can just write this if f and g belongs to L1 and a, b belongs to R, then af plus bg belongs to L1. And you can show that by using the triangle inequality, for instance. And the integral of af plus bg is af plus bg. Yes. Yes. F and G are in L1. Yes. So the first step is to check that you do get something in L1, and that's just by using the triangle inequality, you get this. And everything is finite on this side, therefore this side is finite, and you can conclude that AF plus BG belongs to L1. Oh, if I'm starting to mix my F and G's, we'll have to stop. Okay, and then to actually prove that it's linear, yeah, you have to play with a somehow I don't find that exciting. But you can have a look at the proof. It's not too bad. Okay, and in this class we'll stick to real functions. We won't go into complex. So, because he does everything at the same time. So, one inequality that I'm going to prove is the following one. If f belongs to L1, then the integral of f is less than the integral of the absolute value. The usual inequality of the absolute values that we know is true for Riemann integrals. And the proof is very easy. Yeah. So what we do is the integral of f is, by definition, the integral of f plus minus the integral of f minus. That's our definition. And that, by the triangle inequality, is less than the integral of f plus the integral of f minus. But these two things are positive, so I can get rid of my absolute values. Okay, so this is actually equal to integral of f plus integral of f minus. This is integral of f plus f minus. But this guy is exactly absolute value of f. So we get our absolute value. Okay, another property. So assume that f and g belong to L1. And that f is equal to g almost everywhere. Then for every measurable e, we have that the integral of 1e f is equal to the integral of 1e g. In particular, you can take your E to be the whole space X, and the integral of f is equal to the integral of g. Okay, not that surprising that if your two functions are equal up to null set, then the two integrals are equal. Okay, proof of that. So we look at the difference. And the inequality we just proved tells us that this is less than 1 EF minus G. See, we are always back to positive functions. That's why we do these manipulations. So now, 1E when f minus g is positive, and also it is 0 almost everywhere. That's because f is equal to g almost everywhere. So in order for this thing to be different from 0, I need my f of x to be different from g of x. Therefore, I need my x to belong to the null set. Okay, so that's why I can write this. That's just a consequence of that. And now we, as a consequence of these two properties, we know that the integral of this is 0. And so we're done, because the difference there is 0, and that's what we wanted. So the lemma that we proved last time, not last time, but the time before, is that if f is measurable, positive, and then we have the following equivalence, that the integral of f is 0 if and only if f is 0 almost everywhere. But this works only for positive functions, of course. Okay, there are plenty of functions whose integral is 0 but are not 0 almost everywhere. So that's why it's important. So this I'm pretty sure we proved, and it's something good to remember. Okay, it's very useful. Okay, so that was this. Now the following properties is the converse of this. Assume that the integral of f is equal to the integral of g. So we assume first that f and g are in L1, that the two integrals are equal for every e in M. Then f is equal to g almost everywhere. Okay, so the proof. So we know that the integral of f minus g is equal to 0. And this is true for every measurable set E. Let's take for E the set X where f minus g plus is strictly positive. Why is this a measurable set? I'm sorry? Yes, but the function you have is not quite the function you know. It's a little different. So what you're doing is the difference of two measurable functions, which is measurable, but then you have this plus. How can you explain that the plus thing is not breaking your measurability? Right, but that's not going to give you measurability. Now you can think of this as being a composition, right? Because you do the maximum of a function and 0, and that maximum of two things is a continuous function. So you are taking a difference of two measurable functions, composing from the outside with a continuous function, you get a Borel measurable function. And then you take the inverse image of an open set. Okay? So that's how we know it's measurable. Now, we know this is 0. And what do we know? So, okay. Yeah, the other thing that we should... Okay. So if we do that, this by definition is f minus g plus on E minus f minus g minus on E. Now, what is f minus g minus on E? What's this equal to? What's f minus when f plus is positive? 0. Okay, so we have that h minus of x is 0 when h plus of x is positive. So this part disappears, and we are left with integral of f minus g plus equal to 0. And that tells me that, so how do I conclude here that mu of 0 is, yes, so what this is telling me at this point is that f minus g plus 1e is 0 almost everywhere. That's the lemma I just erased. I have a positive function whose integral is 0. The function is 0 almost everywhere. Now, what does this tell me, actually? It tells me that the measure of E must be 0. Because let's see. If this were so f minus g plus 1e of x is strictly bigger than 0 if and only if x belongs to E. Right? Because if x belongs to E, it means that this guy is strictly positive, and so I have a product of two strictly positive numbers, and it's strictly positive. That's the only one. Okay? So what this is telling me is that this is strictly positive, f minus, or I should write this, if and only if 1e is strictly positive. 1e of x is strictly positive. Okay, so my almost everywhere 0 function is strictly positive if and only if this function is strictly positive. But this is 0 almost everywhere. So this tells me also that 1e must be 0 almost everywhere. And therefore it tells me that E is an offset. So almost everywhere f minus g plus is positive. Now there is nothing particular to f minus g plus. We can redo the whole argument. So we redo this argument with f equal to the x's for which f minus g minus is strictly positive. And we go through the same steps, and we conclude that f is also a null set. Now, if the positive part of a function is null and the negative part of a function is null, it means that the function is null. Okay, the two together means that f minus g is 0 almost everywhere. And we are done. So you see, things are a little more subtle than with positive functions, because now to know that something is 0 almost everywhere, you really need to run your integral over all possible measurable sets. Instead, as before, if your integral is 0, then you know your function is 0 almost everywhere. Okay, so finally you're ready for the main course. I hope you're not too tired. Dominated convergence theorem. So we have a following. Fn converges to f almost everywhere. And we're not assuming any increasing or anything like that, any monotonicity. Second hypothesis, there is, so what do I want here? My Fn must be in L1, right? So we have a sequence Fn in L1. And Fn converges to f almost everywhere. There is g in L1 such that Fn is less than g for every n. And all this implies that the limit of the integral, well, first thing, that f is in L1, and the limit of the integral of Fn is the integral of f. Our favorite conclusion, that we can put our limit inside the term. So that's a theorem that you should compare to the monotone convergence theorem, of course, and to some extent to Fatu, which is very useful in proving this. But the big plus here is that you are not assuming that your functions are positive anymore. It's true in general. Unlike Fatu and unlike the monotone convergence theorem. Okay, proof. The first step is that your Fn in absolute value is less than g by, and this also can be almost everywhere, can't it? Yeah, almost everywhere. That I should put here. So now we pass to the limit and we get f less than g, almost everywhere. Therefore, the integral of f in absolute value is less than the integral of g, which is finite. And this tells me that f must belong to L1. So that's the first part. Second part is to prove the convergence. for this, we are going to use FAT2. We are going to look at the following. We are going to look at G plus Fn. Okay, so G plus Fn is a positive measurable sequence of functions. Okay? Because G must be bigger than minus Fn since it's bigger than the absolute value of Fn. So this is true almost everywhere. So we can apply FAT2 to this, and FAT2 tells us that the integral of the lim inf of G plus Fn is less than the integral of the inf of the integral of a sum. Now this thing converges to G plus F. So I can just replace this by integral of G plus integral of F less than lim inf of integral of G plus integral of Fn. Now what is the lim inf of integral of G plus integral of Fn equal to? I have a constant plus a sequence. What's the lim inf equal to? Well, this is something we haven't proved, but we can, and it's equal to the constant plus the lim inf. Okay, not very difficult to believe, and it's not very difficult to prove. So we can get rid of the G's, and we get one inequality. We get that the integral of F is less than the lim inf of the integral of Fn. Okay, that's already something, a FAT2 type result, but that's not what we want. We want more than that. We want to be able to write that these two things are equal. So instead of using G plus Fn, we use G minus Fn, and we see what happens. Okay, same computation. So we first start by saying that G minus Fn is a positive sequence, and we apply FAT2. Lim inf of G minus Fn is less than lim inf of G minus Fn. Here we have G minus F less than lim inf of G plus lim inf of minus Fn. Well, we say that we could just get rid of this thing. So we get minus the integral less than. So what can you say of lim inf of minus something? It's minus what? Minus lim sub. And so we get that lim sub of Fn is less than F. And now we need to compare this guy to this one. So we can rewrite the double inequality by saying that f is squeezed between the lim sup and the lim inf. Okay, we put the two together and that's what we get. So what can we conclude from that? They need to be equal to each other because we know that the lim inf is always less than the lim sup. So they need to be equal. And of course, then this guy needs to be equal to them because if the two bounds are equal, then in the middle it's equal to. Okay, so the limit exists because the lim sup is equal to the lim inf and is equal to the integral of the limit. So let's do an example. Let's do fn of x equal to sinus of x over n, for instance. And let's look at the limit as n goes to infinity of sinus of x over n over, let's say, the interval 0, 1 with respect to the Lebesgue measure. Can we compute this limit? Does the limit exist? So the big thing is to find the g, to find the dominating function. Okay? And your dominating function needs to be integral. In this case, it's very easy because sinus of x over n is less than 1. The big thing is not to have any n here. Okay? And the same bound must hold, of course, for every n, for the same n. The same bound holds for all n. That's what I mean. Okay, but is one integrable? Well, it depends. It's integrable on 0, 1. Yes. Okay, because if you integrate 1, the Lebesgue measure tells you that this is the measure of 0, 1, which turns out to be 1, which is finite. But if I were doing this problem on 0, infinity, this would not work. Because 1 is not integrable in 0, infinity. Right? If I try to integrate 1 between 0 and infinity, I'm going to find infinity. So it really depends where we are. Okay? So this is a dominating function, and we can apply the dominated convergence theorem, and it tells us that the limit as n goes to infinity is the integral of the limit. So for a fixed x, what's the limit of sine of x over n? 0. Okay, x over n goes to 0, sine of 0 is 0. So we are integrating 0, and the whole integral is 0. Yes, because let's see, there you find a bound which is itself summable and doesn't depend on x. Okay, yeah, that's exactly the same idea. Good. Okay. Now, so let me assign homework for next time. And this is something we haven't really seen. When we say that Fn converges to U uniformly to some f on some space A, it means that the supremum over x belonging to A of Fn x minus f of x, this converges to 0 as n goes to infinity. So to show that a sequence of functions converges uniformly, you first need to compute the supremum for fixed n. You compute the supremum of Fn of x minus f of x. And here, when you take the supremum, of course, you don't get an ax anymore. You get an an, and that thing must go to 0. Okay? The convergence we have been talking about is the pointwise convergence. When we say Fn converges to f pointwise on some A, it means that for every x belonging to A, Fn of x must converge to f of x. Okay, so, and maybe we should do an example. Assume let's look at Fn of x equal to exponential minus nx for, and let's look at the set A between 0 and 1. If, Fn of 0 is 1, and this converges to 1. Fn of x for x strictly positive is, so as n goes to infinity, is going to converge to 0 as n goes to infinity. So you can say that, so define f of x as being 1 for x equals 0 and 0 otherwise. Then you can say that your Fn converges to f pointwise. Okay, that's how you do it. You just fix your x and look at the limit. Now, what about uniform convergence? Well, when you look at Fn of x minus f of x, what do you get? So at 0, you get 0 actually. So what do I want to do here? So what's this? This is exponential minus nx if x is different from 0, and they're both equal to 1 if x is equal to 0. Right? It's either 1 or exponential minus nx. So when I'm looking at the supremum over n of fn of x minus f of x, what is this equal to? Supremum over all x's belonging to 0. What's this supremum equal to? One. It's equal to 1. Okay, the biggest difference you can get is 1. And this doesn't go to 0, of course. So this is an example of a sequence of functions that converge pointwise to f, but not uniformly. Okay, so fn does not converge uniformly to f or to anything else. Just covered one semester of analysis 2 in 10 minutes. That's all you need to know. So, 20 is easy. You just redo dominated convergence theorem. So where were we? Homework. 19, I just talked about. 20. 19 is very easy too. I just wanted to remind you what these terms mean. 20, you imitate what we did. 21. 21 is nice. You need to use 20. And then 22. So 22 is about the counting measure. Yeah, you want to apply this thing to a counting measure. So remember, counting, you just count the points in your set. And actually that's the first thing you should do. You should first prove that the integral of f with respect to the counting measure mu is the series f of k. So this is before doing 22. Prove that. And to prove that, do the 3 steps proof. Okay, start with an indicator, and then a simple function, and finally a positive function. Okay. Now, what is the monotone convergence theorem going to look like, for instance? Well, what the monotone convergence theorem tells you is that if fn is increasing to some f, you can write that the limit of the integral is equal to the integral of a limit, provided your functions are positive. So in this case, we are talking about the series fn k converging to the series f of k as n goes to infinity. Okay, so wherever you have integrals, you are going to have series. And that's the beauty of the Lebesgue integration, is that it's true for any measure, including the counting measure. So all the theorems that we have seen for integrals are actually theorems for series too. So I just stated the monotone convergence theorem tells you that the notation is a little tricky, but if your fn is increasing, meaning that for fixed k, you have that fn of k is less than fn plus 1 of k for every k, then you can say that. Okay, or you can restate this in terms of double sequences. Okay, that's what it is. You cannot avoid two indices. That's the problem here. So I did it for the monotone convergence theorem. Do it for Fatou's lemma and the dominated convergence theorem. I think that's what they ask you in 22. Yeah. Okay. I think I have done enough damage for one day. So let's stop here.
If sigma n converges, then it is Cauchy. So Sn is Cauchy. So in H, so convergent in H. Because we've got the Hilbert space here. We've got the complete norm space. Okay, so that's A. B simply follows by the good old continuity of the inner product. We can write alpha k equals y k. In other words, write y equals the limit Sn. For B, write y equals limit Sn in H. Okay, that means in the norm of H, the limit is holding. So y ek, is that what I wanted? Equals limit Sn ek, n goes to infinity, equals alpha k ek by orthonormality equals alpha k. In other words, when n is sufficiently large, then the kth term is going to appear in the sum, and when I take the inner product with ek, then all the other, this is a finite sum, okay? This is a finite sum, so this is summation j goes from 1 to n, alpha j ek, ej, and then inner product with ek. When I actually do that, assuming that n is big enough that it's past k, which I can always do because I'm fixing k and letting n go to infinity. So fix n big enough that it's past k, then compute this. This simply comes out to be alpha k. All right? By orthonormality. So you're done. K equals limit alpha k. Limit alpha k, limit of a constant. Limit of a constant is the constant. Limit n goes to infinity. Okay. it's the limit of the constant. As long as n is bigger than k, then I have the constant sequence. Before that, it's just 0. Okay, so 0, 0. This limit sequence is 0, 0, 0, 0, 0, 0, then alpha k, alpha k, alpha k, alpha k, all the rest of the way. As soon as n is bigger than k, it becomes alpha k, alpha k, alpha k. You kind of follow what I'm doing there? You can use this. I think you use this on like 10 different problems in this chapter. This trick. Or 10 different problems plus proofs, I guess, combined. Anyway, it gets used all the time. This continuity of the inner product. Okay. So part C is then if x is this converges in H. Well, that's by Bessel's inequality. C by Bessel's inequality. And that's what we actually used in the application. Because what we said was we used by Bessel inequality and A in part A. Because what we said was you've got x squared is greater than or equal to summation x ek squared. Okay. So, and that's, okay, therefore, this is a finite number. Okay? If x is in H, then that's a finite number. Because the norm is finite, okay? So by A, with alpha k, by part A, with alpha k equal to x ek, we have the summation alpha k squared is finite, so then so summation alpha k ek, k goes from 1 to infinity, converges to some y in H. Okay. Converges in what we're thinking about in terms of L2, and converges in L2. So I do get convergence. Okay. I think I'll have to skip the trig series example. You can read up where I get the sum of the reciprocals of the fourth powers of the odd integers. Okay. Okay, I get a formula for that. Classical one. One thing I was going to add to the end of that line was you're going to get convergence. So let me just add the following lines right before I discuss totality, which I didn't get to today. Well, let me just give the definition so that I can say what totality is. Totality an orthonormal set. And now he's going to talk about sets in general, because he wants to consider he can consider the uncountable case almost as easily as he can consider the countable case. There's only a little bit of messing around you have to do. He does a pretty good job with that. I don't want to spend a whole lot of time on it, but I'm just going to go ahead and make the definition here anyway. So I've got an uncountable, a possibly uncountable index set I and kappa instead of k. When he does that, that's a kappa. Lowercase kappa is what that's going to be there. Okay. Is total in an inner product space even. X if M equals the linear span of this orthonormal set, which means you take all possible finite linear combinations, and that's a vector space, right? Take all possible finite linear combinations, and now close it up if M gives M bar equals X. In other words, if the closure of the linear span of these elements is the whole space. Okay. And then we're going to have a theorem about that. Now it turns out that the trig system and the reasoning behind that is simply going to be the same reasoning they give at the beginning of section 3.7.1 for the totality of the Legendre polynomials. It's going to have to do with density. The trig system is total in L0 to pi. So for example, the Fourier series, which I didn't have time to develop here in the notes, for x of t equal the periodic extension of the function of, let's see, what did I take? I took absolute value of t on minus pi pi. So I took a function that looked like this. I'm really out of time now. Shoot. But this was pi, and this was minus pi. Okay, I just took the absolute value of t, and I took this one. In the notes, I did this one, and I developed it as a Fourier series. I found the Fourier series is pi over 2. This goes as pi over 2 minus 4 over pi. It was a cosine series because it's an even function, over 1 plus cosine 3t over 9 plus cosine 5t over 25. So you're getting the reciprocals of the squares. Of the odd integers, okay, plus dot dot dot. Okay, this thing converges in L2 to the x of t, all right, the x of t. And that's all I said in the notes, other than computing what the L2 norm of this is. So by totality, okay, will turn out. Okay, there's nothing more that I can get. I didn't prove this yet. Okay, proof next time. Proof that totality implies convergence in L2 to original function in L2, original in L2, original x in L2 will be by Parseval relation. Proof of Parseval relation. So I left that out. Proof of Parseval relation. So you're going to have to use it this weekend for your homework. Are you feeling that you could do that?
I've seen it before, but
okay.
I don't know if other people have.
So it converges to xt and L2. Now, it turns out, though, this is also uniformly convergent because the reciprocal, let's see, these are the k squared in the bottom, right? So also uniformly convergent. Therefore, what you would have is that you've got the partial sums would be converging uniformly to something, okay, which is in L2 because the continuous function is in L2. And the partial sums would also be converging in L2 to something, okay? But if I have uniform convergence, then it automatically implies L2 convergence. So I would have the partial sums converging, right? Uniform convergence would imply L2 convergence because if you have uniform convergence, you have the difference is less than epsilon. So then the difference of the square would be less than epsilon squared. Take the integral that's less than epsilon squared, and then take a square root less than epsilon. So uniform norm automatically implies L2 norm less than epsilon. Okay, so if I had uniform convergence to y and I had uniform convergence and I had L2 convergence to x, okay, well then it means I have converges to two different things. Well, that's impossible, right? There's only one uniqueness limit. Therefore, y has to equal x in L2. But now if y equals x in L2 and y and x are both continuous, then y equals x. So for a particular example, you can show, using the totality, that indeed this does converge. Okay, to the original function pointwise. So you have xn or Sn minus y L2, well, uniform, infinity goes to 0. You have Sn minus x L2 goes to 0. This implies that Sn minus y L2 goes to 0. Okay, so you have y equals limit Sn equals x in L2. You have two different things potentially which have the same L2 limit. Okay, so that means y equals x in L2. This was a continuous. Both y and x are continuous functions. Therefore, y equals x. Therefore, y equals x. Okay? So in this case, you would get that the series converges by what we've been able to prove. So even though we're not going to do a full thing on Fourier series, at least you can know that your certain classical examples are really good. Okay? As long as you have uniform convergence to the series of Fourier coefficients. Excuse me, absolute convergence. Excuse me. Yeah, I needed absolute convergence of the coefficients, which is a very special case. Absolute convergence of the coefficients, that's not that common, okay? When you just take, if you're just taking any old continuous function, that's not going to be the case. Lots of these Fourier series are conditionally convergent. Yeah. Okay, well, we want to way over. Are there any questions? Last questions? Okay. We still have 2 minutes. Sorry, I thought class got at 1:20. So maybe I kind of hurried through this because I thought we were out of time. So all of this hinges on the totality. This argument here. All of this hinges on the totality. So totality implies this. Okay. This was simply by uniform convergence, okay, where y is a continuous function. Okay, so let me just finish this little argument that I had here, and then we'll leave right on time. This was 5t. Okay, so if I have this series, I can call the partial sums Sn as I did before. Because I have the coefficients are actually absolutely summable. You had, what, summation 1 over 2k plus 1 squared. That's finite, right? All right, and since the cosine is bounded by 1, this is a uniformly convergent series. All right? Sn uniformly convergent to a continuous function. But we only said, well, maybe y is not equal to x. Okay, but we know that Sn converges to x, the original function, by totality. In L2 it converges. Okay, but if I have uniform norm, then that automatically, so if I have integral s, if I have Sn minus y, and I take that squared, and I integrate that 0 to 2 pi, since this is less than epsilon uniformly, this will be less than epsilon squared times 2 pi. Okay, for n greater than or equal to capital N, all right, sub epsilon. So by uniform convergence. So that means that Sn minus y, that's because I'm on a finite interval here, I'm using that. Okay? Therefore, Sn minus y, L2, goes to 0. Okay. So what I had was I had therefore, limit Sn equals x equals y in L2. So I've got the same function in L2. Two continuous functions in L2, we mentioned already they had to be equal. Okay. All right, so we'll do the totality theory next time and finish this thing up. I think you'll be able to do. I did change assignment 3.7 number 3 to an extra credit problem, because it turns out there's pretty fancy manipulation with infinite series. Pretty nasty looking, so I made that an extra credit problem if you get through it. They tell you what the answer should be in the book, so it is doable. But you got to play like crazy with your series.
Both 3 and 6.
Both 3 and 6 are extra credit, yeah. I'm only making you do problem 1 from 3.7.
Yeah, right.
So 3.7 is not the real difficulty. You'll have to read this totality theorem on your own, I guess. Okay. Thank you.